Yeah, thank you for having us here at hardwear.io. Great conference. My name is Steffen, and today I'm co-presenting with Endres. And both of us are researchers from Bochum, myself from Ruhr University in Bochum, and Endres from the Max Planck Institute for Security and Privacy. Our talk is based on an academic paper which was recently published and presented at IEEE S&P in San Francisco. And it deals with the detection of a certain kind of hardware trojans in chips which were manufactured in modern CMOS technologies. This research project, of course, like many of those, is a team effort, so kudos go to Torben, who is in the audience, and Christian, Amir, and Christoph. And one important thing I wanted to mention before is that we open sourced all project-related data, images, algorithms, abstracted design data of chips on GitHub, to allow everybody to redo our experiments or to run their own experiments. And some more information on this will be given out later. So before I start, here comes my one-slide advertisement block. We're from Bochum in the Ruhr area in the west of Germany, which used to be the heart of coal mining. And nowadays we host two large research institutions on cybersecurity. We have like 300 plus researchers. We have like more than 1,000 students, bachelors and masters in cybersecurity. And among those researchers are more than 24 researchers in hardware security as well, cryptographic engineering, site channel protection, reverse engineering, and so on. And we're always looking for industry and academic collaborations on a variety of cybersecurity topics. One thing I specifically wanted to draw your attention to is the Harris workshop, which we hosted in Bochum for the first time this year, where we brought together like more than 90 international participants from academia, industry, and government, who are all interested in hardware reverse engineering, specifically integrated circuit reverse engineering and FPGA reverse engineering. And for next spring, we are planning a second edition. More information will be available under this URL, and you can even sign up for a newsletter and take a look in the program of this year and into some of the talks. Okay, now let me start with some background on hardware trojans. So hardware trojans in general are known as malicious modifications in integrated circuits, which were intentionally inserted by a third party other than the original designer. They could, for example, be inserted to the design right before the chip manufacturing. They were first discussed in a Defense Science Board report on high-performance microchip supply in 2005. And of course, they focused on military-grade hardware and trust into microchips. Payloads of such hardware trojans can range from relatively simple kill switches, breaking the chip, to more sophisticated implementations of trojans leaking cryptographic secrets in specific circumstances, for example. One possible method to realize such hardware trojans is by adding or replacing logic cells, standard cells, in the finished IC design, for example, via engineering change order. So let's consider this scanning electron microscope image tile, which was taken from the backside. It shows various instances of standard cells. So where the single white circles are, those are vias, and the horizontal lines being power lines. So let's say the left one being the original chip and the right one being the one altered. And then on first glance, it's hard to spot the difference between those two pictures. But then here's what appears to be an added logic cell. So in the original, we don't have vias, and on the right side, we have vias in the circle. And here, maybe even more difficult to detect, this is an exchanged logic cell. So it has different via positions here. Now let's also take a closer look at the specific threat model that we consider in this work. So nowadays, many IC design houses operate fabless, and they typically send their finished IC designs to contract manufacturers, which then fabricates the actual wafer containing the chips. So this distributed supply chain, of course, makes chip manufacturing more affordable. However, the fab could potentially tamper with the design data just before manufacturing. And at the same time, it would be possible that another entity alters a design during the shipping to the fab. So those are exactly the scenarios which are already described by the Department of Defense in 2005. And one way to detect such changes would be to commission an external analysis lab, which then verifies that the chips returned from the fab actually correspond to the original design. So as such, our main research question here is how efficiently such an analysis lab could detect those kind of trojans in realistic circumstances. So to minimize any potential biases in the Trojan detection, we strictly separated the researchers in a red and a blue team. So in our specific case, we utilized chips that had already been manufactured. So the evil red team had to use a little trick. Instead of inserting the changes into the chip design before manufacturing, they modified the design file of the already manufactured chip in a way that similar differences exist between the design file and the chip, and thus closely emulating the original scenario. And I will provide the details in just a minute. And then those previously manufactured chips and the manipulated design files were then handed to the blue team, which acted as the analysis lab and aimed to detect the inserted manipulations by comparing the design files and the SAM images of the manufactured chips. And afterwards, of course, the red team confirmed the findings. So now let's have a closer look at the chips and how the manipulations were introduced by the red team. So these are the designs that if you attended Torben's talk yesterday, you might have seen them before, which we use for our case studies. And they have technology sizes of 90, 65, 40, and 28 nanometers, and dimensions of up to 2 by 2 millimeters. And on top, we can see a size comparison of such a die and a 1-cent coin. So they're pretty small, right? Those chips are ideal for Trojan detection because they contain a lot of standard cell-based logic. And at the same time, this is the reason for modifying the design file instead, simply because the chips were already manufactured. So how did the Trojan emulation work in detail? Coming back to the example from the beginning, a typical Trojan insertion could consist of additional logic cells or replace logic cells on the chip. Now the red team emulates these manipulations by modifying the design file of the already produced chips. So first, which you can see on top, the red team emulates these manipulations, the additional cells, by replacing an existing cell with an empty space in the design file. And therefore, if you compare design with chip, it appears as an added cell, right? And for the replaced cell scenario, they could exchange a cell with another cell from the cell library, for instance, replacing a NOR gate with an AND gate. And for each chip, the red team introduced 4 additions and 6 replacements at random positions, scattered over the whole design. And in total, this is, of course, just a fraction of a percent of affected cells. So finding these is like searching for a needle in the haystack. So with this, let me hand over to Endres, who will explain the blue team's perspective and analysis.
Yeah, right. So now that all the preparation is done, the blue team can easily take over. And first of all, the blue team receives physical samples of the chips as well as the design files, and now needs to somehow verify the consistency between them. For that, first of all, the chips need to be imaged. For imaging, it's important to know that the general build-up of an IC looks something like that. On the lowest layers, there's the transistor level where all the logic cells are located. Yeah? And on the more top layers, there's a 3-dimensional electrical routing that connects different cells together. And as we are interested in finding modifications of the cells, we have to put the chip under the microscope upside down to be able to image it from the back side. Now, before imaging, as you might have learned in the workshop yesterday about chip decapsulation, it would be required to decapsulate the chip first, but for us it wasn't really required as the chip was already bare die. So we simply milled down some remaining silicon from the backside, and any remaining silicon then was later on removed with wet chemical etching. Then, after the preparation, the chips could be imaged with a scanning electron microscope, and this is quite a time-consuming and expensive process, as this takes quite a while, like 1 or 2 days to image such a chip in our case study. After imaging, now high-resolution images of all the chips were received. They consist out of thousands of individual tile images and are stitched together to form a large mosaic of the whole chip. They total to a file size of 300 gigabytes of uncompressed grayscale images with resolutions of down to 4.8 nanometers per pixel. When zooming in now, rows of cells as well as the individual cells can be seen, and one could also clearly see that even though we use the same scanning electron microscope, all the 4 chips look quite a bit different due to varying properties of process technologies in this case. Now that these images have been taken, the blue team is able to process images of every cell and compare them to the design file. What is required for that task, though? So first of all, the coordinates of each cell in the design have to be gathered. Also, the precise position of every image has to be known, and then a translation between the coordinates is possible, with which every single cell of the design file can be cut out in the images. This cutout can then be fed into various detection and comparison algorithms. To get the cell coordinates from the GDS2 design file, there are existing libraries like GDSPy for Python that can do the job. In the end, every bounding box, including a label consisting of either the chip type or empty space, is returned. Then to get the coordinates of the tile images, it's essentially the task of the stitching tools like MIST, microscope image stitching, to export position information for each tile in the mosaic. Having now these two coordinate systems in our code, we're able to calculate positions of each cell in the microscope images. That's basically done with a rule of 3 or proportional lookups. However, as physical images are not aligned perfectly, we correct slight offsets using a 4-point perspective transformation to improve positioning significantly. Now every single cell can be precisely cut out of the microscope images and is ready for further processing. So to find additional cells that should not be there according to the design file, detecting base features of cells such as wires can be utilized. Wires are contact points between cell and routing layers and are not deployed in any empty space. For cell replacements, though, this is not enough as the features are there anyway, just at other positions. So we utilize template matching here to actually compare visual appearance of cells. To detect wires, it's useful that SEM images, they always stand out as white bright spots. So with binary thresholding and then correlating it with a round gradient, it's possible to detect them very well, even if the image quality is not the best, as shown on the top right. Though in a few cases there are some wires detected where there are not, certainly, but that's just a few cases, right? And if a cell has been detected to contain any wire, it cannot be empty space, so it has to be a standard cell. As said, for finding cell replacement, template matching is utilized here that compares image based on their looking appearance. In this example, the first occurrence of the cell type is considered to be a golden reference model. Then the second cell of the same type is found and then compared to the first one, and they look quite similar, so they don't get detected as a modification. The third cell instead looks a bit different, so it will be detected as a modification. However, also template matching has its limits when using very similar looking cells here. So when just having very tiny differences, they still fail to detect. In these cases, we again utilize our wire detector on both the reference and the candidate and correlate artificially generated wire masks against each other. With that, even difficult cases that failed to detect before can be found now. Now I would like to show a quick live demonstration, and for that I just connect my Linux laptop here, which should be quite fast. So, alright, so running our algorithms now, it first is loading all the bounding boxes out of the GDS2 design file, which is taking some time because it's already computing all the transformations and translations. And yeah, it's quite unoptimized Python code, so it's taking some while, but can be easily optimized to use multi-core, for instance. And then when this is finished, then which should be like in 2 seconds hopefully, the actual algorithm will start to look for wires in the tile images. Come on. That's like 500,000 bounding boxes. Yeah. So now it's starting to detect like the orientation of the image, and then starts to detect all the bias in each individual tile image. And now in a couple of tiles, it will actually find some positive result. So here it shows now a full tile image with orange boxes being empty space and blue boxes being actual functional logic. And as you can see down here, there's an orange box which clearly contains some bias. So it will be detected as an additional cell. Now I'm switching to the template matching detection, and now I'm looking at the edge of the chip where we expect now some changes. So it will be a bit faster now. And so now every functional cell is compared against every other cell, and here it also found one cell that has certainly been replaced. In the end, it will open up some documents detailing the results we have found here, so you can later on scroll through them and find if there are any false positives or not. For instance, on the replacements, you can see both the cell instance as well as the golden reference template here. And with that, that concludes our live demonstration, and I would hand back to Steffen.
All right, thanks, Endres. And now let's take a look at our results. So how did the detection algorithms actually perform? And for this, let's first review some chip statistics. So all 4 chips contain between hundreds of thousands up to 1.5 million cells on areas between 1 and 2 square millimeters. And our results here show that the algorithms can detect the inserted manipulations almost perfectly. So for the added cells, all instances could be detected with only a handful, 4 handfuls of false positives in the lower technology sizes. With the replaced cells, it's a little bit more difficult. If we tolerate a small 3-digit number of false positives, which had to be checked manually, which could be done, in a matter of minutes to hours, all manipulated cells could be detected for the 90 nanometers, the 65 nanometers, and the 40 nanometers technology. However, in the 3 cases of the 28 nanometer chip, very similar looking cells could not be found. We checked retrospectively with the red team, and to detect these, we would have had to tolerate more than 70k false positives. So, while image acquisition with the scanning electron microscope depicts a notable bottleneck in our experiments, with runtimes between 1 and 2 days, the total runtime of our unoptimized algorithms, and you just saw it in Endres' live demo, was in the matter of hours on a laptop computer. So let's take a look at some of the detected manipulations here for each technology size. So we do not show the cell additions here, as they could be detected more or less flawlessly, basically whenever a wire was showing up in a bounding box, which should have been empty. So here we can see one of the detected cell replacement for each chip. And on the top row, there are the golden templates, while on the bottom row, there are the actual cell instances. And through the difference, although the differences appear to be relatively easy to spot when looking at this slide, it would require huge efforts to find these among hundreds of thousands by hand. However, not everything is perfect, as we can see in these images. So let's take a look at some of the false positives which had to be sorted out manually as not being manipulations. So here some dust or debris settled down on the chip samples, thus covering the cell layout. While in the larger text sizes on the left side, this sometimes led to single blurry cells or a few blurry cells. On the right side, we can see an example of the 28 nanometer chip where several cells are covered. And this is partially due to the fact that we had no clean room environment available for imaging the chips. And to solve this issue, those areas would have to be imaged a second time, potentially even with fresh images. So finally, here's an example of one of the 3 false negative results, so an undetected manipulation in the 28 nanometer chip. And as we all can see here, the cells are looking very similar. However, they do differ and do implement different cell types. As I mentioned before, to find these as well, the threshold value for the template matching would need to be adjusted. such that the false positive rate increases dramatically. So this is where the limits are with our current algorithms and imaging setup. Yeah, one thing that also may play a role here is the increasing complexity of the standard cell library with shrinking feature sizes. So probably improved algorithms, for example, based on machine learning or images from a better SEM environment could improve our detection rate. So to conclude, additional cells can be detected straightforward, while replaced cells yield a bit more problems in smaller, more complex chip technology. Detection can likely be further improved by advanced setup of algorithms, but given sufficient image quality, it is possible to detect such hardware trojans with added or replaced cells that were inserted before manufacturing step or during shipping of the design. Even the smallest hardware trojans, only tampering with a single cell, can then be spotted using classical image processing. As I said, like in the beginning, we would like to emphasize that we released all chip images, anonymized design files, and our algorithm for further research in this area in our GitHub repository. And if you're interested in more details, please take a look into our paper. Use our data for your own studies, and maybe you can even beat our detection rate or can improve on it. There's one more thing after my conclusion. So we would like to leverage the fact that we have you here as a hardware security expert audience, and we would like to hear your opinion. So this is why we have a one-sheet paper survey, which is available at the registration. You can also drop it off there. It consists of 7 multiple-choice questions. It's completely anonymous, and we basically would like to hear, like, from you regarding the relevance of hardware obfuscation and Trojans for the hardware security community. You would doing me a great favor if you could fill this out. So with this, here's a summary of what we did, and we're looking forward to your questions. So, did you want to repeat?
Yeah, I'm just asking about the size of the Trojan that you already inserted. How many gates?
I mean, we inserted 10 gates per chip, or we inserted 4 where filler cells were, and we exchanged 6, so 10 gates in total per chip. But we would argue that those are like standalone hardware Trojans. So the academic literature says you could already implement a hardware Trojan with a single gate. I don't think this is realistic. The realistic Trojans, which we see in the literature, consists, probably of hundreds of gates, but we have like a minimal border here, right? I mean, if we can detect every single instance, we can definitely detect those larger kind of Trojans.
My second question is related to the countermeasure. I don't know if you highlighted this in your presentation about if you propose any countermeasures for this kind of attacks.
I mean, we do detection here. We want countermeasures against Trojan insertion, right? So what we need to do here, the literature holds like a lot of countermeasures, but we haven't seen a real Trojan insertion here. So what we need to do here is actually do a study where we actually insert a meaningful Trojan. Those were emulations, right? We need a design which we don't know, and then we need to reverse engineer it, insert a meaningful Trojan, and then, we can test all the mitigation strategies and all the countermeasures from the literature and see if they hold, right? I mean, there are ideas like split manufacturing, for example, would be just to mention one.
Thank you. Anyone? Question? Okay, thank you.